And we are back in business. All right, today we are going to talk about equilibrium expressions involving pressures. Last class, we talked about equilibrium expressions involving concentrations, and that is either represented by the expression Kc, or sometimes you'll just see it as K. Now, for equilibrium expressions involving pressures, it is represented as Kp. And both of these fall under the umbrella. These are both equilibrium expressions, or Keq. So just like Kc was the concentrations of all the products over the concentrations of all the reactants, Kp is the same thing, just now using the pressure of the products over the pressure of the reactants. And same thing, whatever that coefficient is, that becomes the exponent when writing the equilibrium expression. Okay, so much, and last thing, much like Kc was unitless, even though each individual concentration is measured in molarity, moles over liters. Same with Kp, even though most of those pressures will be represented by atmospheres or torrs or millimeters of mercury, still this equilibrium expression, Kp, for pressures is unitless. So that means Kp is written just as it is for Kc, or K. So this would be the expression for K or Kc. So it's the same thing for the Kp expression. We take our pressure of our product, not of our reactant, and raise it to the second power, since that coefficient there is 2. Over the reactants, there's no coefficient next to N2, but then the pressure of H2 raised to the third power. So just like for Kc, Kc is the equilibrium concentrations, Kp are the equilibrium partial pressure of gases. And normally for expressions written with Kp, since we're talking about pressure, normally these will be for reactions involving gases. And then for Kc, it'll either be concentrations of gases or of solutions, or of aqueous solutions. Okay, so you should be able to write for any reaction the equilibrium expression, whether it be Kc or Kp. Then much like what we did for Kc, where we calculated it out when given the concentrations, you should be able to do the same thing if given the equilibrium pressures of each of the reactants and products. So using what we set up on the last slide, using that equation, now we should be able to input each of those into our formula here and get our final answer for Kp. And keep in mind, this is still unitless. Okay, it is not in atmospheres. Okay, so you should be able to calculate Kp for any reaction if given all of those equilibrium partial pressures. Now we're going to see the relationship between K, or Kc, and Kp. And we can derive that relationship from the ideal gas law. So if you remember, the ideal gas law is PV equals nRT. Okay. And let's say here we want to solve for pressure, because we're talking about Kp. So pressure is nRT over V, the volume. And we know here, if we concentrate on this first part, we think about, okay, what is N, moles over volume measured in liters? So moles over liters, that's our concentration, which is measured in molarity. So we can think about this in terms of molarity times R times T, or we could represent that molarity by just a general term of concentration, C. Okay, so that means, so pressure is concentration times R times T. So if we are solving that one if we rewrite this in terms of our values of K, that can be converted to Kp, and then this C, that's Kc times RT. Or we could rearrange that and solve for Kc, where that would be Kp over RT. The only thing that we have to add here is we have to take into account that not all of the reactants and or products will be gases. So what we have to do here is we have to include the fact that the number of moles of products, of gaseous products, might not necessarily be equal to the moles of gaseous reactants. So that delta N, the change in the number of moles, that represents the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. So keep in mind it's products not minus reactants, not reactants minus products. So if that's different, that means the values of Kp and K, or Kc, will be different. However, if delta N, if the number of moles of products of gas and reactants are equal, if delta N is 0, the sums of both sides are identical, that means this RT term cancels out, and that means Kp will be equal to Kc. And remember here, for our units of R, you'll always be given this. You were using the 0.08206 value, since we're still talking about volume in liters, pressure in atmospheres, and the temperature will always be in Kelvin. So if it's given to you in Celsius, make sure you convert it to Kelvin. Okay, so using the example we just did, the Haber process, the production of NH3, we got this value of Kp. Now, we want to calculate for Kc. Oops. So we use this equation, and what we can do as well is rearrange it and solve for K, or Kc. It's Kp over RT to the delta N. Okay, and we know Kp already 3.9 times 10 to the 4th. R is always given to us. Temperature, you have to convert this to Kelvin, add 273, so that's 308. And then the delta N here, you look, the number of gaseous products is 2. 2 and 3, and then the number of moles of gaseous reactants is 1 plus 3, so 4. So that means delta N here is -2, not just 2. Okay. And keep in mind, if for like N2, if this was aqueous, for example, that means the number of moles of gaseous reactants would be 3. So keep in mind, you're only taking into account the moles of gases, whether they're products or reactants. Okay, so then when you calculate this all out, you get a K, or Kc value, of 2.5 times 10 to the 7th power. Okay, so you should be able to now calculate for any Kp value And if given Kc, you should also be able to use that, calculate for Kp using this relationship. All right, that's all for now. See you next time.